Hello, everyone. In this video, I will be going over the dyadic growth curve. So for those of you who are familiar with growth modeling, particularly within SCM framework, including linear growth modeling, as well as parallel process growth models, or bivariate growth models, as they're sometimes called, where you're modeling two constructs within an individual. This will look fairly familiar. We are just going to make just a couple of tweaks, and we are going to estimate the growth process across husbands and wives. So we'll be using a sample of just under 630 couples from the PairFam data, who provided complete data just for ease of analysis. And so I will walk you through the Mplus syntax. So up here we have our title, and oftentimes this is where I will make notes. You'll see me comment out some things in the syntax, but more general comments I will actually include in the title. Issues with data, non-positive definite matrix inversion problems. Perhaps I'm using 3 or 4 or 5 different data files running the same model, perhaps as a sensitivity analysis. And so I will label my data files in here. You can use the title again for whatever kind of notes that you want to make within your analysis. So when you return to it after not working on it for however long, you don't have to kind of catch yourself up. And so we have a data command, and so this is just file equals data.dat. And for those of you who are not familiar with Mplus, if you have your data file and your input file, your syntax file within the same folder, you can just name your data file, because Mplus will automatically look within that folder. So I will show you what that looks like very briefly. And so we can go to the external hard drive that everything is located on. And so we have a computer backup, and then we have papers, growth curve, we'll go into Mplus, distinguishable dyads, and here is my input file, and we have our data file as well. All right. And so up here at the top. And so this is what I recommend. Otherwise, you're going to have to manually specify the path in which you are going to, where your data file is. So I've always found it to be easier just to keep it all in one place. So here are the variables within my data file. I have an ID variable, an age variable for each partner. We have anchor and partner. So anchor is the primary respondent within PairFam, and the partner is their spouse. So our anchor could be either a male or a female, and obviously the partner could obviously be a male or a female, since they've recruited both males and females as the primary respondent. And then I did some data cleaning to create a male and a female file. So what we have here is we have F for female, we have support, and then we have the wave in PairFam in which it was measured. And so we have support and strain at wave 2 for females, support and strain at wave 3, and so on and so forth. So we will only be using the support variables. And so that's why I have this use variables code right here. And so I'm telling Mplus to only use these 8 variables. We will be using robust maximum likelihood with Yuan and Bentler corrections, which provides a scaling correction factor to address non-normality in our residuals. And it also provides an adjustment to the chi-square statistic. Right, and it provides accurate standard errors. And so moving into the model command, we have M support int and M slop. So this means male, this means support, and this means the intercept. And so in Mplus, you specify the intercept first, then you specify the slope. So it's the male slope or male support, and then that's the slope. All right. And then you use this vertical pipe here, and you specify only the slope latent construct. Again, so in latent variable growth curve modeling, or latent curve modeling as it's sometimes called, we fix our factor loadings to indicate time, whereas if you're familiar with more multi-level, you actually have a time variable. So we do not have a time variable here, so we use our factor loadings to indicate time or wave. And there was roughly a 1 year lag between waves. And so we start out with wave 0, and we fix that to 0, and then we fix the next one to 1, to 2, and to 3. So Mplus will automatically create your intercept factor for you. So you do not need to hard code it. You certainly have the option to, if you would like, but that is not necessary. And as you can see here, I'm specifying the linear growth in marital support for the male participants. And down here is just identical to the male participants, and we just specify a intercept for the female partners and a slope for the female partners, and we code it again in an identical way. If you wanted to hard code your intercepts, it would look something like this. So you would scroll down, you would include this, and we would fix every loading to be 1. All right. So this would be hard coding your intercept factor, and you would just do that for both. And so there's the female intercept, and this is the male intercept. All right. So this is what the syntax would look like. Again, it's 2 extra lines of code. So this is a little bit of a shortcut, but you may have specific reasons for doing it the long way. I actually prefer it this way, so I can kind of know what's going on in my model a little bit more precisely. And so what we're going to specify next is the covariances between the intercept and slope factors. So marital partners, each partner within a dyad is nested within that dyad. So you have male partner nested within the relationship, and you have female partner nested within the relationship. And so those means and those slopes are probably going to be correlated in some way. Perhaps if we were doing like a parallel growth model or a bivariate growth model, where you have within one person 2 different growth factors, you might not believe that the slopes are correlated with one another. You might actually believe that the slopes are actually uncorrelated with one another, and they occur independently. And so in that case, you wouldn't want to estimate that covariance. Instead, you'd actually fix it to 0. But when you're doing with dyadic data, even if these the covariances are not significant, I always recommend keeping them in because it effectively captures the non-independence of the data. And without that specification, if you do set it to 0, those constraints, then you can see ripple effects in other aspects of your model. And so that can, in an extreme circumstance, lead to different substantive conclusions, alter your p-values, alter significance levels, alter parameter estimates, and things of that nature. So I always recommend maintaining those covariances, especially in dyadic data. And we just correlate each one with every other one. So the male intercept, the male slope, the female intercept, and the female slope with exactly those same variables. And this is just a quick way to specify covariances within Mplus. You could manually code them much like you would in a correlation matrix. So you could do something like this. And you could do this in numerous lines of code. But again, for brief reasons, creating this one line of code tends to be easier. But these, this and this are essentially equivalent. And Mplus won't give you any errors since you are specifying in the intercept of males being correlated with the intercept of males. It's not going to do anything with that parameter, so you don't have to worry about any errors. Unlike the bivariate growth model, again, in many circumstances, we are actually going to correlate these errors of the observed indicators across partner at each time point. So again, we're correlating the intercept and the slope, so where each dyad member is at time 1, as well as their trajectory. Those are going to be intercorrelated. But we might also have interdependence in the residuals of the male and female supports that might be correlated with one another. There might be factors outside of this change process that we're specifying that is provides information about why male and female support would be correlated with one another. All right, so it might be that there's other than just the overall change process, there might be something that just happened at wave 2 that would increase or perhaps decrease the residual covariances between support between the male and female partners. For example, let's say the couple just had a child diagnosed with a terminal illness, for example, that could actually increase the residuals for the spouses, because they might be more supportive of one another than they usually are, because of this kind of external process that is kind of that is unique and outside that kind of growth process. So we do want to keep these with statements, these covariances at each wave. If you want to test whether or not they're the same across waves, you can absolutely do that. So if you throw in these equality constraints by using these labels, then you can empirically test whether or not the extent to which the spouses co-vary over time is the same. So we're not going to do that in this demonstration, but that is entirely possible if you have a theoretical rationale for why the residuals would be constant over time. And so finally, we're going to go into the plot command. We want to take a look at the marital support across time. So we have plot 3, which gives you the most information. That's kind of the default I use. And then we're going to create series, and then we're going to create the observe variable, and then we're going to place it in context of the slope variable that we got from right here. All right. And so output tends to be fairly straightforward. So we want to do tech 1 and tech 4, residual to look at the residual matrix, or the expected minus the observed covariance matrix. We want SAMstat, and we want to standardize our variables, particularly to understand and identify what is our explained variance in our observed variables. How well is the intercept and slope factor accounting for the variation in those individual reports of support across reporter and over time. And then we can go ahead and we can run this. And so we can scroll down, we can ignore all of these. These are just, Mplus is reacting to some of the syntax being longer than 90 characters, but it doesn't pose any problems to the estimation of the model. So we'll scroll over here just to kind of get a gander at what what is happening in our model, looking at sample statistics to see whether or not these results look correct. Oftentimes I'll go here first just to be sure that I am not miscoding something. Perhaps I forgot to include a missing data label or whatever it might be. But oftentimes I will see that syntax error in my univariate statistics. And we can also kind of get a general sense of what is happening in the slopes and in the perhaps even of the intercepts. So we look here and we have M support is 14.87, then 14.65, then 14.36, and 14.34. So we can begin to see using our observed data rather than our estimated data. This is the raw data. There is somewhat of a decline for male support across the study. And so for female support, we have 15.24 and then 14.97, and then it goes slightly up again to 15.09, and then it goes down again at 14.65. And so again, we're seeing this general trend where on average, there are these declines in marital support over this 4-year period using the PairFam data. So we will scroll down. We will look at our chi-square test of model fit. So we have 18 degrees of freedom, and we have a chi-square test of 33.43. So this is significant, but this test tends to be highly sensitive and will detect extremely small differences between your observed and your expected covariance matrix. And so I don't place a whole lot of weight on the test of model fit. I instead use a Gestalt approach where I'll integrate the CFI, the TLI, the RMSEA, the SRMR, and other local fit indices. So our RMSEA and CFI and TLI are looking really, really good. We have a 90% confidence interval that our RMSEA value is between 0.16 and 0.056. So that's really strong. And we have a good chance of having a good RMSEA. And one of the things I'm looking for is how spread out this value is. Because you can have an RMSEA of 0.037, but if your 90% confidence interval is, 0.008 and 0.22, then there's a lot of variability in the RMSEA. And that doesn't necessarily say that your model will be well-fitting. We have CFI and TLI are 0.99. So again, generally, those are going to be accepted cutoffs. And then our SRMR is 0.037. Again, so everything is looking good. And all things considered, we have a really strong model data fit, which you tend to have in dyadic data anyways, because everything is going to be correlated in some way, shape, and form, either through a covariance or a regression coefficient. So you tend to get a lot of really strong model data fit within dyadic research. So here are the fixed values. Here's our intercept, and here's our fixed values for time for the males, and the same thing for the females. And then here are the covariances between our intercept and slope factors. So we see that not many are actually correlated with one another. In fact, the intercepts, both of them, are correlated significantly. So the higher that males are at time 1 in terms of marital support, the higher their partner is at time 1 in terms of marital support. Right, so that's how that would be interpreted. But again, we don't really see any other significant kind of covariances. Again, all of these are unstandardized, and so we need to be careful with our interpretation because these are in the raw metric. All right, so looking down here, we have a few other maybe ones that are significant in terms of the covariances between male and female reports. And so male support and female support were correlated at wave 2 together at 0.001. So these, again, these are the correlations that we specified up here. That's these guys right here, all right? And so we find them to be significant here, and they are significant here. But as you can see, I had talked about constraining those paths. My guess would be is that constraining all of those paths to be equal would result in a significant decrease in model data fit, just looking at how much stronger these are correlated at wave 2 compared to wave 3, 4, and 5. So the means is of substantive interest here. Oftentimes in latent variable modeling, we don't care as much about the means, but when you are doing growth curve analysis, the means are of a significant importance. And so here is the mean of male support, that's the intercept. So this is the average levels, the model implied estimates of the average levels of male support at time 1, and that's a raw score of 14.87. And then we see the same thing for females, support in the intercept, 15.24. All right, and those are significantly different than 0. All right, so that's our significance value. In growth curve modeling, we'd probably want this to be significant. I'd actually be fairly curious to know, to think about variables that you would not expect the value of time 1 to be significantly different from 0, but perhaps there are research questions in which that is, highly relevant and perhaps even expected. And so the significance of the means is nice to have, but to me, it's not all that consequential in our analyses, in our interpretations. On the other hand, the slopes, those means are incredibly important. And so what this indicates, this is the male slope of support over this 4-year period, and it's negative. So that means, as we recall looking at the descriptives, that male support over this 4-year period tends to decline in a fairly linear manner. We might be able to check like a quadratic to see if there's a nonlinear effect. But we'll actually take a look at some of the plots, and we'll see that this tends to be a fairly linear decline. And this is where we want our slope to be significantly different than 0. If this slope is not significant, then that means that the declines that we are seeing in male support are not significantly different from 0, and you would interpret kind of the same way as you would like a regression coefficient that's not significant. And we would say, although there are declines in male perceptions of marital support with their partner across the study period, it was not significantly different from 0. And so we essentially are saying that there is a kind of a straight line across male support on an XY axis, where you have time on the X and slope on the Y. You would see a horizontal line. And so likewise, we have declines in support for females as well, and it's roughly the same magnitude, and we can actually constrain these to be equal and to test whether or not the slopes are different. And we have the exact same findings as males. So women in this study also report declines in partner support over the study period, and there is this it is significantly different from 0. All right. So another really important characteristic of growth curve modeling are the variances. And so oftentimes we are going to want to include a covariate or a predictor that is accounting for variation in the intercept and or the slope. And so in order for us to do that, for us to include like age or relationship length or depressive symptoms as predictors of intercept and slope, we actually have to have a significant amount of variance. Otherwise, that means that slope line, this negative 161, if there's not a significant amount of variance, is the same for every person in the study. And so that is saying people on average, they do not vary in the declines in marital support over this 4-year period. So stated another way, that the rates of change in marital support declines is constant for everybody in the study. Right, so we have significant variance in the intercepts, which again, if we want to predict them, that's good. They're not of as much interest. And we see that we do have some variance in the slopes, but technically the male support is not significant. It's hovering just above that p equals 0.05 level. And you can see that the female slope is also hovering just about that p equals 0.05 level. So we're pretty close in terms of the variance being significant. And so I might actually proceed with including covariates, because oftentimes if you throw a covariate in there, the variance estimates will change once you account for a certain amount of that variance, and this can move to significance. So you're going to have some people who argue if it's not significant, then you shouldn't touch it, and this is the end of your analysis. I would tend to poke and prod the model a little bit more to see, and I proceed with my hypothesized model to see if anything changes, to see if any of those predictors become significant predictors of that variation in the slope. All right. And so we also have our residual variances down here. And so it's always good to look at the standardized loadings. So for the intercept, we can see this is for males, that all of these standardized values are the same, which means that we've done a good job at identifying the intercept, and it is accounting for the same amount, roughly the same amount of variance in our repeated measures of marital support over time. If we saw this at 0.62 and then this jumped to 0.82, 0.81, or in 0.80, that would signify some potential problems in using this methods, and that's something you would need to take a look at. Likewise, we want to take a look at the slopes, and you will see that they are positive, even though we found that the slope declines. These are those values, or the intensity, or the magnitude of the slope. So you will see them be positive. And as you can see, they are roughly linear. So 0.12, 0.24, 0.36, quite linear actually. Likewise, down here, we also have a linear slope. Again, sometimes these values can be a little out of whack, which will tell you that maybe you have a quadratic form, or maybe if you're doing a lot of waves, maybe there's a spline model, or a cubic model, or some other type of effect is going to be the best way to reproduce the characteristics of your data. It's always nice to report standardized covariances or correlations in your results, but for the most part, I report unstandardized effects. And so here is, again, the extent to which our male and female reports of support within a wave are correlated with one another. And as you can see, again, at wave 2, we have 0.62. And so this could be a method effect, actually, because from my recollection, don't quote me on this, is that the repeated measures of support and strain and of the marital characteristics actually started at wave 2. I don't believe that occurred in wave 1. And so this might actually be an artifact of, or a selection effect, that people who approved that their partner could be contacted to participate in the study, those anchor people approved their partner to be included. Those people are probably going to be, perhaps they're happier in their relationship. Perhaps they don't mind talking about their relationship because overall and on average, they're fairly solid. And then as we see over time, that begins to, that disattenuates, although we do actually see a little bit of an increase in the correlation between male and female reports over time. So there might be actually some meaningful interpretations of these covariances depending on your research question. And then finally, the thing I look for is the R squared And our model is doing, actually a really nice job at accounting for the variance in support and strain over time. So essentially, this is the dyadic growth curve. We might check the residual output just to be sure that we're not misspecifying anything. And it looks like overall we got a couple that we're underestimating this effect here, and we are underestimating this effect here. So there's something wonky going on, perhaps with male support at time 4, and that's something we would want to look into. Because these are kind of outlying z-scores right here, and they are significant. But essentially, without going too much into the ideas of local misfit, it's just kind of, again, a brief introduction to know that these are underestimated, these negative values, and that's something that would potentially be meaningful and perhaps could be a source where your substantive conclusions might change. For example, one of them might be that after figuring out why we have these significant z-scores, that might actually have implications for the slope. So remember, is 0.078. If we adjust our model and perhaps there's an outlier, perhaps there's something going on in the data, and we address that, and these go down to below significance, or they're not sticking out like sore thumbs, then we might actually have a significant slope, and that variation that is marginally significant becomes fully significant. So that's something you would want to, again, take a look at, but that's just a brief introduction to the residual matrix and local misfit within the context of a dyadic growth curve model. So hopefully this video has been helpful to you in estimating and learning more about some of the underpinnings of the dyadic growth curve, as well as the estimation of the dyadic growth curve within Mplus.